How you guys doing today?
Good.
All right. All right. A little bit. Air of enthusiasm. Cool. I got no business to talk about. Anybody have questions about anything, assignments, anything? All right. Cool. Well, let's recap where we left off. I want to hear from you guys. Guys, make sure that I know your name. If I don't know your name, that's the problem. The attendance is only worth 10% of your grade, but that's still an entire letter grade for you. Um, And I wish I could say I'm great with names, but it is not the case. So, if I don't know your name, just tell me your name again. It's good. Unless I call you by name, I probably don't know your name. But I'm learning. Okay. End rant. Somebody tell me where we left off. What happened last time? Yes. Lydia. Yes. Thank you. We talked a lot about time. So where did we start and where did we end with time?
I got a little confused all over the place, but
Okay. Let's see if we can put it in order.
that just stood out to me was we were talking about how there could be two types of like personal time and talk
Yeah, that was interesting. Okay, any other thoughts on that? Yeah,
I
has
think
it? Yep.
I think I think that we had started we're talking about like how time can like change, but our perception of it changing might be more related to like the atoms in the clock being changed by like an effect of gravity or something like that.
Measurements, yeah.
Actual time being changed, and that's kind of how we got into like the different perceptions of time.
Yeah, there's a very internal experience with time, and then there's like this measurement side of things. And then there's the little t in all of our equations too, which corresponds to our measurement time, which is where things start to get really interesting. Yeah.
Where the 0 point was and how you would get there, but we calculated it.
Wait, the 0 point.
Where the
Oh, yeah, the right ascension. Yes, I'm gonna try to clarify that even more in a minute. We'll see. Yeah, related to latitude and longitude, exactly. Sorry, Maritz, I'm looking for your name on this chart. Oh, here we go. Yes, so we still had a few more things to scrape together about how the sky is divided up, and it had to do with the path of the sun throughout the year, basically the elevation that it makes, right? So you probably noticed that the sun is lower in the sky in the winter. It actually crosses over the celestial equator, right, which is all relative to the North Pole, that celestial equator, not the same as the true equator. And so the sun's going to dip across that, and this crossing marks the point in the sky at that moment in the Earth's orbit where we will set the right ascension point, which is somewhat arbitrary, but yeah.
Since you're talking about dividing up the sky, I was thinking about we talked about the Sumerians and why they like to count things by 60.
Oh yeah,
And I think you posed the question, why would we divide a circle up into 360 degrees?
yeah,
Right?
yeah.
If you think about it, that's comes from like base 12 mathematics. So,
Honestly, the Sumerians were base 60.
but it just
Yeah.
by a product of that, base 12, or in this case, base 16, has more whole number factors. So if they weren't,
Whole number
then base 10.
factors. Okay,
Right,
break
so
that
like
break
you
that down for
divide
me.
12 by 3 or 4,
Oh, I see, I
by
see, I see,
2,
I see, I see.
or by 6.
Yeah.
Right. So it's easier to divide things into whole sections rather than
Well,
deal with fractions.
you could divide 10 into 10 though. 10 ones into a 10 unit clock still.
But does that give you the granularity that you need when you're dealing with?
And then you'd have individual tens in between them. Tenths.
But then you're dealing with fractions, and you're dealing with.
But they still do fractions. They just call them minutes and seconds and stuff
Sure.
instead.
It was just a thought.
It's a thought. I mean, this is people wrestle with this stuff.
Sure.
I've heard that the Sumerians did it because you have three knuckles on your or three segments on your hands, and so I'd have to think about this really hard for a second. But there was some sort of counting system regarding the.
So if you look at your segments of your fingers,
Yeah.
you hold up 4 fingers, you
Okay.
can count to 12 in the same way that you would count to 10 on 2 hands. You just count the segments of your fingers.
There you go.
you
And
get to
then
12.
maybe you can do a score with the thumb or something like that. do two groupings of it. I don't know. It's pretty crazy. I actually just think the really crazy part is we're still using 6,000-year-old Sumerian system for, but we don't use it for anything else, which is really fascinating. Did you ever hear that?
It was because you counted with your thumb.
Oh, with your thumb. Good call. Good call. Remind me your name again. What's your name again? Ellie. That's right. Yeah, it's pretty crazy. I love it. I love these.
For so long though was because we had used it for so long that we just kept using it because everyone else used it. So
Well, I think they were some of the first, at least in, so for some reason, the East and the West were like really cut off from each other. And I'm still like trying to make sense of all of this, but there's some geographic barriers. In other words, like China and Japan, Korea, they have like a very different history with these ideas and arrived at many of the same ideas very differently. But in the West, it seems like the first geometers perhaps were the Sumerians. And by the way, maybe it was the Indus Valley civilization. Maybe the Sumerians came from them, but we don't know because nobody has decoded the Indus Valley script. But the more you study the ancient Indian civilizations, the more they start to look like Sumerians, or the Sumerians culturally start to look like the Indus Valley civilization. It's like, it's very hard to discern that. But my thought is that the Greeks became obsessed with logic and geometry and all of these things that they in some sense inherited from the Sumerians, maybe from the Indus Valley civilization. And so there's just kind of this carrying over of, what would you say, formalisms, which the Romans are obsessed with the Greeks. They took it. The European monastic, the roots of this place, the roots of universities, they were obsessed with the Romans and the Greeks. And anyways, it just all comes down. And today we have clocks on the wall that have 60 minutes in an hour. Yeah. But that's kind of interesting. So we do need to actually today build out a couple more pieces of the time story, just because it's kind of, there's a couple more conundrums people have solved over the years, we kind of happen in the background like this. We don't really pay attention to them, but I think they're worth pointing out. So we'll get on that. What else? Ezra, yeah. Ezra, right?
Yeah. I have a question.
Yes.
It'd be better to explain it on the board. Could I
Ooh,
go?
absolutely. I love it. Yeah.
So I've thought about this.
Come over here though, because it'll show up in the camera better.
Okay, so here's that lift, right?
Okay.
Let's say you can move faster than light, about 2 times faster than light. This way.
Okay.
So you're here 2 times faster than light, right?
See, yeah.
If you looked back at the Earth,
Hmm.
would you see something that's about I don't know the exact measurement, but would you see something that was there before you left? Because you technically.
Well, the light wouldn't have reached you. It would be hard to see something without light is the problem. So if you're outpacing light, then the signal you wouldn't see anything. It would just be black, I suppose.
You wouldn't see anything until it hits you.
But it will never hit you if you're moving faster than light.
I mean, if you stop.
Oh, you stop.
You stop. Yeah, you're moving twice as fast as light, and then you stop.
And then 2 seconds later, yeah, sure. So we see the moon. What the moon looked like 2 seconds ago, or something, for instance, or however long it takes. You'd have to look that up.
Do you think there's anything like else behind that could like contradict this at all?
What do you mean, behind it?
Like, I mean, I don't know if we move faster than the speed of light, we could.
Well, so one of the really frustrating postulates of modern physics, in some sense, is that nothing can move faster than the speed of light. Now, this is a huge problem, of course, because like clearly parts of the atom must move faster than the speed of light because the atom is vibrating at some speed, which tells us about the light itself. So the question is, can groups of atoms move faster than light? And there's no evidence that they can right now.
But the atoms themselves do.
Maybe the pieces of the atoms themselves do, because light is perhaps a dance that the atoms are acting out with one another, some sort of a transactional dance that the atoms are playing out. So maybe the pieces do of the atom. In fact, there's good reason. I can build that out. We're actually going to spend some time on the concept of light here I think in a week or something. When we'll deal with telescopes. I know we're a bit behind where you guys are at in the textbook, but light's worth making sense of. It's pretty bizarre. But I think light's best thought of as some sort of actual material handshake between atoms. I really think I encourage you to start thinking about all of these weird mysteries, light, electricity, magnetism, gravity, as network effects of atoms relaying some sort of tensions or pressures to one another, to their nearest neighbor. There's no magical need for them to do anything crazy. Atoms have extended structure to them. These processes don't have to be so mysterious, and we can start to look at the nuances of that. But needless to say, all material bodies that can deform have substructure, right? So if I was super strong and I just crushed my steel water bottle here in my hand, right? It's like theoretically possible. Or if I had a vice, I could deform this, right? Now, why can I do that? Well, I can do that because there's a lattice of, let's say, iron atoms in here, and I can bend the subunits out of shape, right? So I can give it a new form, I can deform it. The atom also deforms, right? So we know that the atom is actually doing some sort of oscillatory behavior. We'd have to unpack the specifics of it, but it's changing shape. Its surface is moving in some sort of way which is oscillatory.
What is the actual atom?
Well, its position changes, its location. Inside of here, its location changes. So like deformation requires that you have subunits, is what I'm trying to get at with here. The atom also must have subunits also, if you if you are willing to consider that the atom must be a material object. It must also have subunits. And so as it acts out this dance of light, I think that the dance of light and its particular speed tells us about the rate at which it can deform. So in some sense, the subunits can only change position at some rates, which probably reflects their material properties to some extent. Like, if I slam my hand on the table right now, there's going to be a wave of deformation that travels down this. You might call it, it's sort of like a sound wave, but it's really called a phonon. But it's really just the lattice atoms are being deformed. There's going to be actually a dissipation. So if I put a microphone down here, there's going to be a characteristic speed at which this wave is going to travel. So I hit my hand, I'll hit my hand down here, travels to the microphone down here. There's a characteristic rate at which this material can be deformed. This is the case.
Easier in fluids.
Yeah, so the material properties, exactly. So the material properties are going to dictate the speed of that. And it has a lot to do with the stiffness and the density of the material that dictates that. So I think that the speed of light, in some sense, and this will come back to this because we're going to do light, give it its full due justice, but the speed of light tells us something about the actual substructure, the material substructure of reality, its ability to deform. It's really telling us about that material's properties in some sense, because we can learn about its stiffness and its density as a result of that speed. It's really, really fast. It's really, really fast. So it's probably something that's extremely stiff and really low density, because that's the fastest waves that you can get in materials for the most part. Which makes sense, because there doesn't appear to be a lot of stuff in between here and the moon. So something with really low density, something that's really, really stiff. Okay, that was quite a derailleur, but we'll circle back to these topics. It's an interesting question. I like how you're thinking. It's good. Any other loose ends from last class before we plow on? Yes, remind me. Sarah, yes. I know I should know your name. You're always here and participating, and I'm just awful, and I apologize. Okay.
Like, I'm an English major, so I thought like linguistic option.
Nice. Let's go.
Where did the word sidereal?
Sidereal. I always struggle with how to pronounce that word. Sidereal? I don't know. Could you like Google it for us and try to? I've always wondered that too. That's a great question that I don't know the answer to. I don't even know how to say it, so that's even worse. I think it's sidereal. I used to say sidereal, and one of my students corrected me, but we never looked up the etymology. That would be really interesting.
Sidereal.
Yeah.
So there's no syllable between.
Sidereal.
Oh, it is.
Yeah.
Sidereal.
Do you guys remember what sidereal or sidereal or whatever it is? Do you guys remember what that means? Like sidereal. We talked about this right at the end of class. Anybody remember? What's the difference between sidereal time and solar time? Like a sidereal day and a solar day.
Difference between basically when the stars are in the same point versus when the sun comes to the same point.
Yeah. And do you remember why they're different?
Because our We have moved around the sun a little bit more compared to our rotation.
Yeah, we got to turn a little bit more to face the sun because we're kind of running. What would you say? Running away from it in some sense. Yeah. Although we're in orbit, but yeah, that's true. Did you figure it out, Sarah? Not yet. Sidereal. Yeah, I don't know. All right, we'll get back to that. Any other loose ends? So, all right. So we for whatever reason, I'm kind of moving along according to the textbook. I'm a bit behind, but we need to talk about we need to talk basically about bigger cycles now. We need to talk about climate. We need to talk about weather. Yeah. Okay.
So it's sidereal.
Sidereal. Okay.
It says mid-16th century, partly from obsolete French sidereal, partly
French.
Latin.
Okay.
But it looks like it kind of popped up during like the rise.
What is the French? Is it for stars or something?
It's SYDEREAL. I don't know any.
And it doesn't say what that prefix means? Interesting. All right. Well, if anybody figures it out, bonus respect. All right. What's that?
Multiple phones popped up at once.
Yeah, figure it out. Let's see what we can do. I don't know. There's got to be some delineation of that root. Maybe we can get to the bottom of it. It's always interesting where words come from. A lot of our words come from German. I don't know. You can learn a lot about the history of colonialism and how different countries have, because you spread your language around. It's actually it's part of the battle in some sense. Yeah, Isaac.
It says that part of it, the Latin part anyway, of like Sidereus,
Hmm.
starry astral of the constellation.
Okay, that checks out. Star stuff. All right. Yeah, English is a wild language when you start to dig into it. We have a lot of little pieces from the Romans, but there's a lot of stuff from the Germans because the Germans invaded England at some point, right? The Norman invasion and all of that. And yeah, there's a whole story. I am not an expert in it, but it's fascinating. All right, so we need to do climate today, and climate is, one of those topics which actually it used to be like 1 out of every 5 science stories in the news. It just doesn't seem to be like people care about the climate anymore as much. So this is, I was actually kind of, yeah, it's maybe it was easier to talk about this in the past because people had a lot more opinions about things. But there's something interesting in the whole climate study because it really starts, I think it's the first, maybe the only time in this class that we really get to see the interface of like politics and science in some sense, right? And what's that? Yeah, it's getting real. But not just politics, but also just, interests, people's sense of obligation to the natural world, people's sense of, uh, what should we say? Impact, like things like this. There's a lot of really interesting pieces of this puzzle, and I want to get your guys' perspective on them. I mean, I think one of the things that we're going to see cropping up over and over again is that people have an inherent sense that nothing happens in a vacuum, right? So everything that's happening in the world is in some sense interacting with everything else, and this gets quite complex. And so, I think another piece of the puzzle that's going to be quite interesting is that climate, especially climate on Earth, has been crazy. If we're going to look over millions of years, right? Today, we're going to see that, and the story for how these things have changed is actually really incoherent at this point. I mean, we're getting into the cutting edge of what people understand in some sense. We're going to talk about the glaciation cycles, also pretty bizarre stuff, right? And even the best theories that people have proposed, let's say the standard narratives, the textbook stories, they leave a lot wanting in some sense. But we do know that some pretty crazy stuff happens on our planet, right? We have these huge glaciers that come down and retreat on this kind of regular clockwork 100,000-year cycle. But that just started like 2.5 million years ago or something. That's pretty weird. The planet that the dinosaurs inhabited was a very, very different planet. It was a really high CO2 atmosphere, really, really hot planet, no polar ice caps. What the heck? Very, very different world. This whole story just gets more and more compounded. So anyways, that's just a preview of what we're going to dig into here in a few minutes. But I want to polish up along the way a couple of loose ends that we didn't quite get to. And I think these are worth pointing out because you'll encounter these in your everyday life. So back to our time story. People kept track of time. We talked about all the sorts of different ways that people kept track of time. Generally speaking, for most of human history, at least in terms of the concept of keeping time and making appointments and so forth, people basically used solar time. This is that when the sun rises is kind of sets your day, right? And guess what? When the sun is overhead, that's noon, right? Now, you can imagine that that would work out pretty well for making appointments if you lived in the same town with somebody, right? Because the sun's overhead at approximately the same time for everybody because you're all in a small geographic location. But what happened was that when people started making mechanical clocks like these, um, every town basically started having a clock in it, right? Clocks became really popular, except the clocks would all be slightly different than one another because the sun was in a different position over every single town, ever so slightly differently, right? And so this made a huge problem at some point, especially in the 1800s when people began to have train stations and be actually trying to make appointments in other places and have the trains meet up with one another and all of this, right? Because you can't just have it be noon when the sun is overhead anymore. It just doesn't work out. Everybody's going to have a slightly different time. So they essentially averaged the solar time and they chopped the world up into these things, right? Time zones, which are pretty crazy. So I don't have a ton to say about this, but I want you guys to understand why we do this to ourselves, which can get really insane. So some of these time zones are really wild. So China is on its own time zone, right? So you could be at like the far western side of China, let's say in Tibet, and I think in Tibet it's I have to look. I can't remember which way this goes. Let's think about this. I want to say the sun rises when it's basically late morning in Beijing or something like that, right? So it's getting on close to noon by the time in Beijing by the time the sun rises in Tibet, but they're all still on the same time zone, so it's pretty bizarre. So in some sense, the time zones are made to try to keep people on the same page with respect to appointments and schedules and things like that. But it is in some sense rather arbitrary because the actual astronomical time is not something that can be standardized. There's also this really funny feature too, which is the date line, right? I don't know if you guys have any friends or family members who live on the other side of the date line. It's always the funniest. Like when I schedule podcasts with people in Australia or Japan or something, it's it's always really tricky. It kind of breaks my brain because the days don't line up when you make appointments with these people, right? But you have to start over at some point, right? And they decided to draw this line right down the middle of the Pacific Ocean because, any guesses? Yeah.
Because like almost half the planet is covered by the Pacific Ocean.
Yeah, nobody lives there. Yeah. I mean, not nobody, but relatively speaking, right? It's a very depopulated region of the Earth, and so you're going to sort of screw with the least number of people by drawing a day in between them. So yeah, these are all very interesting conventions. They're all in some sense compromises that we've had to make. Okay, I thought that was worth pointing out just to be practical. Seasons. Okay, so we're moving towards talking about climate, but we have to recap on seasons. So seasons, weather, climate, these are all sort of jumbled up related ideas. In some sense, there's cycles to this, nested cycles, but they're in different scales, right? So seasons, this is kind of what, a pattern that of weather, let's say, something like that, that happens on an annual basis, right? Whereas climate is kind of patterns, what we could say, of weather in the same way that happen on a much bigger scale, right? But there's something very cyclic to all of these processes. When we started the class, I pointed out to you how why it is, and I said, if you learn anything in this class, maybe this would be something that's worth taking on, because most people, you talk to them on the street, they seem to think that the reason that it's hot in the summer is because we're closest to the sun. Remember, that is not true at all. We are actually further, in the northern hemisphere, we are further from the sun in the summer. So the, does anybody remember the name of this? The oval aspect? What's that?
Elliptical.
Elliptical, yeah, we call it, there's a word for it in astronomy, to how elliptical it is. Do you remember? An adjective? Starts with an E also.
The eccentricity.
Eccentricity, yeah, exactly. So the eccentricity for the Earth is something like 3%. It's almost a perfect circle, but it's not quite. I mean, the distance that we vary is like 3%, right? And that turns out to be nothing compared to the tilt of the Earth, which is, you know, on the order of 23.5 degrees. So the eccentricity just doesn't matter that much. Now, this is going to come into play later when we talk about, hold on to that thought, because when we start talking about the cause of these glacial cycles, we're going to run into this crisis again, where we're in some sense blaming some of this cyclicity on eccentricities that don't seem to have the power to really do much. So there's some cool mysteries in this discussion today. Maybe one of you guys will solve one of them. Okay, so you get less, you're not leaning into the sun as much in the winter in the northern hemisphere. You get less sun as a result of it. What else is different about the summer versus the winter? We're starting to feel some of this, yeah.
Like the sun, the path of the sun is much more overhead. So there's like a lot longer time for the sun to be out during the day. So you like feel it's raised a lot.
Yeah, the path I think is really, really important for many reasons. One of them has to do with the amount of time that you're exposed to, right? The days are longer, right?
And then also like there's a word for it too. I'm blanking on it now, but like since it's more overhead, it's more of like a direct sunlight.
Exactly, yeah.
In the winter, it's more. Yeah, so
We got a picture for that one. This one's kind of interesting. Yeah, I hadn't really thought too much about that one until I read it actually in the textbook. So yeah, they're more, the rays are lower intensity and more oblique, right? They're just more spread out, you can see essentially, right? So that's kind of interesting. There's also, what else happens? So we talked about this a little bit when it came to, I forget why we mentioned this before. Why else would those oblique rays be kind of weakened? Can you guys think of anything? Yeah.
You have to travel a little farther.
Through what?
The atmosphere.
Yeah. So the atmosphere really does take, how should I say this? It drains the juice out of light, right? Light gets scattered through the atmosphere. And you can think about it again. Start thinking about light. Start thinking about these things in terms of network events. Start thinking about them in terms of relay. The light has to be relayed from one atom to the next, to the next, to the next. Each one has the potential to sort of dissipate some of the juice away from the puzzle, right? Some of the energy, some of that zip. And that's what happens in the winter. And we're going to start experiencing that more and more. And it will make us all feel like hibernating more and more, I fear. All right, one other thing I wanted to show you guys, this might clarify the right ascension thing maybe a little bit too. Again, you can see that in the summer that the sun, this is just in the reference point of that celestial sphere. That the sun's arc appears to be higher in the sky, right? This is what we're talking about, the sun's more overhead. But in the winter, it kind of crosses by, actually this is the equinox over here in March. And in September, you can see that it actually crosses the celestial equator. And that's that moment in the spring when they actually mark the position of the stars for the right ascension. So I think this illustration maybe does better justice for how the sun's path changes in the celestial sphere over the course of the year, which is really kind of bizarre to imagine. Does that make sense? Okay. Couple of other interesting pieces of this puzzle too that I think are worth going over. Because we do have these seasonal changes, right? So, and I wish I have a nice animation, but we'll get back to it in a minute. So every year, there is some sort of polar ice, right, that expands and contracts. And this has to do with the way that the northern hemisphere or the southern hemisphere lean into the sunlight. So we actually chop the Earth up to reflect some of this, right? We actually define some of these pieces of the puzzle according to the way that they get light or don't get light during these equinoxes, right, or the solstices when the orbit's at one of its maximums, right? So, for instance, you guys have probably heard of the term the Arctic Circle. What the heck is the Arctic Circle? Anybody? Yeah.
It's a circle on the north.
Oh, come on, you can do better than that. Yeah.
Based on this image, it looks like that is the portion on the northern end of the planet that will be fully in darkness in winter for the northern hemisphere and fully in light.
That's exactly right.
for summer.
Exactly. Yeah. So the place where they draw that little circle is the last place where you're going to get a full day of light or darkness, depending on which side of the orbit you're on. That make sense? Now, what about those tropic things? You guys have probably heard of the tropics, right? What's up with the tropics? Yeah.
The place is closest to the equator.
What's the limit? Why do they draw them where they draw them?
Is that where you can always see those star signs? That don't like the night of the day.
See this.
Like Tropic of Cancer, can you always see Cancer in the sky?
Oh, that's an interesting question. I don't know about that.
Just a guess, I'm not.
Yeah. Well, I was gonna say that the way they define the limits of the tropics is because at the summer solstice, the sun is actually directly overhead with you. So you can see this is kind of drawn at that moment, and you can see that the sunlight is directly overhead at noon on the summer solstice there. The equator actually isn't directly overhead, but the equator, of course, is smack dab between both tropics, so it's kind of still the hottest place on average because it's getting both the northern summer and the southern summer. It's sort of smack dab in the middle of them. Does that make sense? Cool. All right, so I don't know. Those are kind of interesting pieces. You're going to hear these terms that are
stretched most. So we're not full perfect sphere. We're a little.
That is true too. That is true too. It is an obloid sphere. That speaking of eccentricities, though, it's even less. It's darn near a perfect sphere. It's actually it's pretty incredible. Not as good as the sun though, which is almost perfect, which is weird. We should talk about that sometime. Okay, so anyways, same thing happens down south. It's just a different set of tropics, different set of Arctics, Antarctic Circle, Tropic of Capricorn. I pulled some movies. Let me see if these will play. This is pretty cool. So yeah, so you can see when you're up there in the Arctic Circle, you know, in winter, it's dark. This is it's pretty dark all winter. They're not quite at the North Pole, right? And it isn't quite the solstice. But yeah, all day long, June 21st, full daylight, which I guess can be quite maddening. I've only known one person who lives up there in the Arctic Circle, and she said it was quite depressing actually in the winter and had to leave eventually. Yeah. Oh, cool.
And it's a little south.
Mm.
Tammy.
Yeah, yeah.
But yeah, it's really cool to watch the sun in the summer and the winter. And in the winter, it's just like this across the So it's pretty epic, honestly.
Yeah.
Like just sunrise and
Yeah.
sunset.
Was it depressing in the winter though?
I mean, there's like 4 to 5 feet of snow where we live, so it's a little depressing. Yeah.
I don't know.
A homebody, or not. I guess it's what it comes down to.
Yeah, yeah. I guess if you can manage to get some artificial light. I mean, some people have real physiological.
Vitamin D.
Yeah.
It's like the Alaskans and the natives, And salmon actually
Mm.
so much vitamin D.
Mm.
So salmon kind of kept up clear and stuff.
Heck yeah, I'd smoke salmon
It's
for
slightly
lunch.
depressing, suppose.
Yeah. I mean, yeah, people actually have persisted in those climates for a long time. It's kind of nuts, actually.
It's a lot busier up there, and people rely on the climate or the seasons in a whole different way. And so
Hmm,
you spend the whole summer being so busy, which is like spring and summer are like 3 months together.
mm-hmm.
Gardening, and they get the hugest produce and everything because of the way that the sun is up. It just never sets on.
Interesting. Are you less sleepy in the summertime?
Um, maybe it'll be midnight and the sun's still way up in the sky.
So crazy, yeah.
Yeah, I had to get blackout curtains because I have a child. So
Mm.
it was hard for him.
Yeah,
So yeah, blackout curtains.
that's freaking crazy.
Yeah.
I don't know. I'd love to see it. I haven't been up there, but I would love to see it. Let's see what else. I think I got one more movie of this. What is this? Oh, we're gonna get some bad music as well. We don't need that. I believe this is North Pole summer, where the sun doesn't set. So kind of similar to what you're talking about, but this is, I think, even closer to the North Pole, maybe. But yeah, pretty freaking wild. So everybody on Earth has a kind of different experience with this whole thing. I actually just think it's wild, like that people down south are having the inverted experience to us. It's really strange and hard to remember. I always think about that when it comes to like something like Christmas decorations or something. Like I haven't spent a lot of time. I've been to South America once, but I haven't spent a lot of time down there. But I assume, yeah, just totally inverted. Yeah.
Something that I do think is interesting is how the majority of humans and human civilization is generally above the equator in the northern hemisphere than the southern. Like, and that goes for like most of the continents. Like most of the land is above that point.
Yeah, except for Africa and South America. But yeah, in terms of like, yeah, industrial civilizations and stuff, for sure, especially in modern times.
Well, even with Africa, most of the largest part of Africa is in the north, not the south.
Yeah.
Pure landmass.
Yeah, and certainly in terms of like ancient civilizations like Egypt and Somalia, stuff like that was in the northern hemisphere. I guess the Mesoamericans had the Incans down south, but not really an industrial civilization. But yeah, it's a fair point. It's a fair point. When we keep talking about Western civilization and stuff, it's all in the northern hemisphere for sure. I guess even Eastern civilization is all in the northern hemisphere too, like China, ancient China, Japan, all that. Wait, is Japan in the north? In this north? I'd have
It's in
to.
the north.
Yeah.
Yeah, it's very
Okay.
north.
Good. Never been there. I need to go to Japan.
They've been more north than us.
Significantly.
This is a little off topic, but I'm kind of reminded by it because of the fact that it's just getting a lot more sunlight, right? And in certain days, so it must be warmer. It implies it's warm.
Yes, summer. Yeah.
Do you know if satellites actually have to take that into account, like how much sunlight they're getting, and like what materials they need to be built out of?
Ooh. I mean, I don't know the answer to that. I don't know much about satellite design, to be honest with you. I don't even know the path of the orbit. My guess is that I have no idea, man. I should know the answer to that. Does anybody know anything about satellites? Do they all orbit the equator? Yeah.
They don't all over the equator.
Okay.
There's almost, even though the sky looks very clear to us, there's not a lot of space left in the sky.
I've seen the pictures. Yeah, there's thousands of these things up there. Yeah.
30 feet.
Yeah, it's wild. And trash too.
They all orbit in different places. Most of them, their orbits deteriorate over
Yeah.
yada yada. But basically, the difference is so marginal because of how fast they're moving around the planet. It just doesn't really affect them that much.
But they're all at different latitudes. They're all at different latitudes, is what you're saying.
Most of them orbit vertically around the Earth.
Really? That's insane. Are you serious? We need
the geocentric one.
over vertically over the poles.
Yeah, generally that direction.
This is how little I know about satellites. What do you guys? Can you share?
Well, I mean, this is just like a complete guess, but I feel like they probably would, or like they would take into account like the absolute hottest that the satellite would be able to like take in at any point in its orbit, so that it wouldn't, like, when it gets colder or whatever it is, like when the temperature's changing, like it wouldn't affect it in that way. Like it would never get to the point where you're like you would build it for like the absolute hottest. That makes sense. Like
Yeah, you would think that if they're going faster than the Earth is turning, then it wouldn't so much matter because they will just get half light and half not light all the time.
That makes sense. I'm more thinking like, if you were to have like a satellite that's like,
Geostationary.
it's like going around the sun.
Oh,
like
oh.
eventually catch on fire.
Oh, yeah, there are some of those. They usually park them at these little there's these nice little balancing points throughout the solar system where you can just park stuff because it's getting equal amounts of tug from different bodies at the same time. Um, Usually, we call these, with respect to the Earth-Moon system, they call them Lagrange points. So you can just park satellites in these places. There's a nice, like Jupiter has its own one of these little wells. They're like just little low points. And it tends to accumulate a lot of asteroids in those. And so there's two of those. So there's these nice little tricks you can play where you can park satellites and they just hang out there at some, pretty stationary, like relatively fixed points in these orbital systems.
What do you think? Pretty good sense.
Well, you guys know more about satellites than me. Fair enough. Yeah.
Sort of remember about satellites is anytime I've ever seen like pictures of satellites, they are the shiniest chrome silver boxes. They're probably reflecting most of the light away.
Yeah, you can see them at night for sure.
That's why I said they didn't really have much of a difference.
Yeah, they probably are super reflective.
Calculations they do about the sun is mostly regarded to solar panels because those are mostly how they're powered
Right.
continuously. Because I mean, the sun's right there. There's no atmosphere to block it, so
And that is also a really good point. Yeah, so the atmosphere eats up a lot of light, like we were talking about.
Radiation is actually more of a concern than temperature. We're pretty good at dealing with temperature. So we understand how to reflect light and how to disperse it. But the radiation from the sun can actually interfere and it can like change the bits of memory in a computer system from one to another, and it can actually modify the data of an actual.
Yeah, there's really gnarly high speed stuff. Let's say high speed particles for now. I'll come back to that. But there's really, really, really high energy collisions going on outside of the atmosphere. There is a nice little protective piece of the puzzle, which is our magnetic field, and we're going to talk about that in depth here eventually, which saves a lot of us. But the atmosphere certainly saves us from a lot of that as well. Water is a great absorber of all this stuff for sure. Yeah.
you- bringing up the magnetic field, that is exactly how most of the satellites are protected.
Mm-hmm.
They stay just below. Most of them are below or within the magnetic field, so
That's
that
right.
most of that radiation is blocked.
Yeah.
Because the remaining radiation is stuff that generally they can just reflect or deal with, but they can't deal with it if, say, there's a solar flare.
Yeah, it can get overloaded for sure.
Or something like that. Then, or magnetic storm, something like that, something that surges beyond its normal, tolerances. Then, yeah,
It is absolutely true. We have to make it to climate today because we're gonna barely make it through this course otherwise. One more thing to say though about the atmosphere, it actually messes up your idea of where even the sun is at any given point because there's some refraction. You guys ever like go fishing or something and notice like when you have a change in density of a medium like in the atmosphere versus outer space, you actually get those rays getting refracted, right? Which is again, think networks and relay. The light is actually getting bent as a result of it. And so that can actually mess with your picture of where the sun is. So at the equinoxes, the sun actually sets and rises a little bit longer than exactly 12 hours, and it has to do with the position of the sun due to the atmospheric refraction. So that's another interesting piece of the puzzle. One other really interesting piece of the puzzle. Have you guys ever noticed? I noticed this because I go swimming in the river here all the time. That when is it actually the hottest in Oregon?
Like August.
Right? Which is kind of weird because the solstice, the most sunlight is June. What's up with that? And yeah, Sarah.
It takes time to, just instantly.
Yeah.
Water out.
Yeah. Yeah, absolutely. Yeah, it's not crazy. Does anybody know the term, the $10 word term for what that's called?
Thermominence.
Oh, that's good too. I was gonna use a different one though. Hysteresis. That's a good one. Write that one down. You can impress your friends. Hysteresis. Hysteresis, it just means that there is some lag in the signal that is the response to some sort of forcing drive. So you have a drive signal, in this case, the sun, maximum insolation, let's say, and then you have a delay in the response of the system to that, right? And in this case, yes, like Sarah says, you have to actually heat up all of the different pieces of the system, right? It takes a while, though, to get all of these pieces up to temperature. And so, yeah, the result is that the best time to go swimming is actually in August, not in June. But it's kind of bizarre that it works out that way. And so this process of hysteresis actually is going to play a huge part in many of the different processes, especially thermal processes. But it is a very, very common phenomenon in nature where you're going to see stimulus followed by a lag in effect of that process. This will get into our light discussion later too. All right. So now we're inching towards weather and so forth. Because we're talking about heating up the earth, we're talking about cooling down the earth. Yeah, one of the, this is in some sense the basic floor plan for how people think about the weather systems and really climate as well. There's this basic kind of circuit, right? So all this heat comes from the sun. In some sense, we could probably just simplify and say all of the heat that we're really paying attention to comes from the sun. It's not quite true. There's actually a fair amount of heat under our feet as well. But for the purposes of discussing the weather patterns and the climate and so forth, we can think about all of this heat coming from the rays of the sun. So sun, super powerful, insane fusion reactor thing that we don't talk about till next semester. But it's basically jostling all the atoms here on Earth, and the atmosphere is getting all wound up. Some of it that comes down and jostles up the atoms in the river and on the ground. Some of it gets reflected back. Some of that light just, if you look at the moon, the reason the moon is glowing is because it's all reflections, right? That's light leaving off the surface of the moon. The same thing's happening for Earth, right? If you were hanging out on the moon, you would see a lot of light being reflected back to you off the surface of the Earth. So we're losing a lot of light as well. And in fact, we lose, what's that?
Snow blinds you.
Exactly. Snow's a great reflector, right? White is a really, really shiny reflective surface. We'll have to unpack why that is later. But needless to say, what's going to stop the light from getting reflected? It's like clouds for the most part, right? I mean, clouds are an interesting feature because in some sense, clouds happen because you shine light, you heat up bodies of water, the water evaporates, they form clouds, and then the clouds can trap some of the heat. And so you get these really complex cycles of heating and cooling which happen. Once you start building ice caps, now you get the chance for even more reflection, right? So you can get feedback loops. Feedback loops are kind of interesting. They're like a huge part of biology and nature and everything that we're going to be talking about downstream of this. So what's the basic idea with feedback? You guys have heard about feedback before? You ever experienced it? Like if you have a microphone pointed at an amplifier or something, right?
So the output of a system is redirected to the input of the system.
Exactly. So in this case, right, what's the input of the system? The light, right? Sunlight. Well, sunlight some of it might be reflected, but then it's redirected back in, right? If it's captured, that heat doesn't leave. So you can imagine, or sorry, in some sense, the input's getting reflected if you have like a surface, like with the polar ice caps, right? So there's all these reverberating effects. You evaporate water, water makes clouds, clouds keep the heat in, clouds keep the sunlight out. So it can be extremely complex. You can get these second, third, fourth order effects, which are really difficult to pin a simple model on. Like if it sounds like what I'm saying is rambling and insane, it's because there's so many variables here feeding back on one another that it's very difficult to make a simple, succinct statement like, well, the reason that, the weather looks the way it does today is because there's more sun coming in. It's like, it's never ever that simple, right? Now we do have, like I said, we've just got done talking about one of the simplest cycles, which is the annual insolation, the seasons, right? And the weather is different in the summer versus the winter, that's for sure. But there's so many factors for why that's the case. Now, when we start talking about weather over thousands and thousands of years, it gets even weirder, right? Because all of these feedback loops start to add up in bizarre ways. I think Dante mentioned it early, like a different class for some reason, about the albedo effect with respect to the reflection. As these ice caps grow, they reflect more light away into space, which means, was it because of what we were talking about? Do you remember?
Yeah, it was just because them explaining why the moon glows.
Why the moon
even though
glows.
it doesn't actually emit light.
Oh yeah, sure.
That was it.
So we'll cycle back on that in a second, but again, that makes sense. So as the ice caps grow, they get rid of more of the light that's coming in, and that makes it even colder. And then the ice caps grow more, feedback loop again, right? Input is getting amplified, and the output feeds back into the input. So you get colder and colder and colder as these ice caps grow. Well, that's interesting, but then the question becomes like, why do they tilt back in the other direction? Let's look at this for a second. One thing I do want to sort of, I do want to get your guys' input, and I want to kind of weigh in on this, is that, the climate's, there's been these enormous changes in the climate over the past, let's just stick with the past couple millions of years, right? So every 100,000 years or so, we have a huge glacial period where the Earth gets really cold, and then it gets really warm again, right? This is like clockwork. You can predict this. I'll show you some graphs in a second. That's been going on for a really long time. We happen to be in one of those warm periods right now. Presumably, it's going to, who knows when the next cold period is going to happen. I've heard estimates ranging from tomorrow to never. I actually once interviewed trying to get this guy's title right. He's kind of the climate czar for the Obama government, but he's the head of the Goddard Space Sciences Institute, which is actually a building in New York City, of all places. And he told me we were never going to have another glaciation ever again.
Glacial maximum.
Yeah, he told me that was never going to happen because humans had changed the atmosphere to such a degree that wasn't going to happen. And then I mentioned this later in another conversation with a different climate scientist, and then that guy sent me an email and he was like, I didn't say that. And I was like, you did say that. And so I was like, come back to the show and tell me why you don't think that. And he came back and he was like, well, I meant that, if we didn't take a hold of our industries and stuff, that we wouldn't have another one. But we have, so we're going to have another one. So I don't know. It's weird. My point is that people's projections about the future of glaciations are running the entire gamut of possibility space. And it's quite interesting because in some sense, at least the last, my perception of these events has fixated on, it's really in some sense fixated on human contribution to the way that the climate changes. Now, I think that this is in some sense born from a very genuine understanding that humans sometimes don't pay attention to the second and third order effects of their actions, right? I think this is actually something to be really concerned about. However, most of the conversations focus on a single molecule. What molecule is that?
Carbon dioxide.
Carbon dioxide, right. So, this concerns me. Now, like I said, this just hasn't been getting the same kind of news play that it was getting for the previous decade. So maybe nobody's really concerned about this anymore. I think they probably are. But carbon dioxide. Okay, there's a lot of things for sure that people do that I can see when, say, I go for a jog in the morning. I can see a lot of gross stuff that people are doing to the natural landscape. But for whatever reason, people focus on carbon dioxide. Why do they focus on carbon dioxide? Ideas? Anybody? Yeah.
Because it's obvious and it's simple.
Okay.
Easy to point out.
Okay. I think that's part of the puzzle for sure. What? Let's circle back on this. I'll come back to it. So carbon dioxide, what's the deal? Well, carbon dioxide is kind of like those clouds in some sense, right? It acts, in theory, to insulate the planet, right? It's very, very similar to water in that respect. It's what we call a greenhouse gas. So is water. It's a greenhouse gas, right? It kind of makes, you guys have greenhouses or you've worked around greenhouses, you basically keep the heat in, right? Now, I'm a little bit sketched out about this carbon thing, and I'm going to unpack that for you as we go ahead, because in some sense, I think that it's a little bit of a cop-out, because it's the cheapest and easiest thing to clean out of the environment. And I think in some sense, its popularity has to do with the fact that it's easily remediated. The reason that I don't think that that's good enough is, well, let me ask you, how much carbon dioxide is there in the atmosphere? Does anybody know? Wait, I want to hear some projections. Like, what percentage of the atmosphere is carbon dioxide?
60%.
60%. What else?
I'll go with 0.5%.
0.5%. What else?
7.
Let me make sure I nail this exactly right really quick.
It's the spray.
Oops.
I'm pretty sure it's, wow.
What else? 60%. 0.5%. It's actually 0.042%. So that's something like for every 100,000 air molecules, the 42 of them are carbon dioxide. So almost nothing actually. Particularly, okay. Now we're going to come back to that. So there's something though that I think is embedded in this, right? So I'm kind of opening a can of worms, which is that I think in some sense, carbon dioxide is a greenhouse gas, does actually, in some sense, all of our combustion processes do contribute to it, fair enough. So it's also extremely easy and cheap to remediate. You basically make scrubbers, you can get rid of it. If you're a corporation, you can say, hey, we're doing the right thing, we made some scrubbers or whatever. But there's some other pieces of the puzzle that make me really suspicious of just that carbon-centric thing. And it's multivariate, so I'm going to try to keep this as organized as I can. There's a lot of stuff that humans are doing to the environments around them that are really bad for them. They're dumping all sorts of gross hydrocarbons and plastics and toxic endocrine disruptors and all of this stuff. Those things are really, really expensive and would require a complete reconsideration of our material economy to deal with. You can't just make a scrubber to get rid of endocrine disruptors. You got to come up with new plastics technologies. Basically got to stop making everything out of oil. So like everything in this classroom, this desk, your chairs, most of your clothes, they're all made out of oil, right? So there's a lot of things that are screwing up the earth that have nothing, they're not easily remediated, right? So I think it's in some sense, I think the carbon thing is it's quite convenient in some sense to blame everything on it. Yes.
One of my favorite, because I had to talk about this with someone, is the electric car thing, like fad. The reason I'm calling it fad is because it kind of stopped. Is because it was the easiest thing to blame. We already did catalytic converters, which were these things you stuck on the end of your exhaust and basically got rid of the nasty chemicals
Yeah.
from your exhaust gas of your car. They were like, okay, we're going to make electric cars. They don't have emissions. Not true, but it's not. It's less than 1%. We don't need to care about it. Whatever. So we replaced cars that produce some CO2, which is less than 0.42% of the atmosphere and contributes that much less to actual global warming than oxygen or nitrogen. With
Or water.
with a car that is built on one of the rarest, most expensive metals to make, lithium, that requires the burning of oil in
Yeah.
such large quantities
Yeah.
that you release methane
Yeah.
and
Yeah, I think
such
I'm gonna
worse chemicals
I-
just to build one of those.
yeah. I
Is just like, and so, and the thing is, it's similar to like recycling, where it was not an actual solution as much as it was, let's redirect the problem so that people stop, telling us to actually fix the problem. Let's do the cheapest, easiest thing.
I don't want to be too cynical here, but I do think that you're onto something, right? So the alternatives in some sense are these lithium-ion batteries. Those have to be mined by child slaves in the Congo. Like you've really redirected things in such a way that you make the consumer feel good. The corporations get to keep doing all sorts of nasty things. By the way, emissions from cars are really gross, but the thing that's gross about them isn't carbon dioxide. The thing that's gross is the high energy like radicals and stuff that are going to give you lung cancer, right? There's all sorts of nasty stuff. The catalytic converter deals with some of that, right? But there's still gross things coming out of engines that have nothing to do with carbon dioxide. And so this is another point, is I'm like, in some sense, if we get totally, what is it called? Uh, Tunnel vision, yeah. If we get total tunnel vision about this and we get obsessed with one inert molecule that really doesn't pose any health effects to us, we might miss a lot of things that actually are quite dangerous and scary, and we really should be demanding that these companies clean up about their products. And so, okay, so the way I see it is that there's a genuine, as human beings, we all have a real genuine sense of wanting to be in balance with our cosmos and be in harmony with the world that we live in. People like having trees out. They like living in nature. There's genuine health effects of these. I would say for most of human history, we worshipped nature to some extent. It was a very animated, alive universe. And I think that in some sense, these non-human entities, really these like economic entities, like these massive corporations, have found a way to sort of harness people's compassion to get what they want, which is to please their shareholders and stuff like that. I mean, they're really just giant algorithms that are crunching along, making money, and that's fine and well and good. The problem is sometimes it can come into conflict with what's actually good for us as people. So case in point is like, when I was a kid, there was all these books coming out about how really introducing, this was the first book, it's called The End of Nature, and it really introduced the public to the concept of global warming for the first time. And again, it's motivated by this like real understanding that like, hey, we're doing these industrial processes that are perhaps getting out of control. The problem is they can often sort of go off the rails with that to some extent, that they actually come across as deeply anti-human. So, I dug up this book review. This is a book review. I think he wrote, this is either the back of this book, where they have a little blurb. And this is actually the chief scientist from the National Forest Department who wrote this review. And he writes it this way. He says, McKibben's a biocentrist, and so am I. We're not interested in the utility of particular species or the free-flowing river or ecosystem to mankind. They have intrinsic value, more value to me than another human body or a billion of them. Human happiness, and certainly human fecundity, are not as important as a wild and healthy planet. I know social scientists who remind me that people are part of nature, but it isn't true. Somewhere along the line, about 1 billion years ago, maybe half that, we quit the contract and became a cancer. We have become a plague upon ourselves and upon the earth. It is cosmically unlikely that the developed world will choose to end its orgy of fossil fuel energy consumption, and the third world its suicidal consumption of landscape. Until such a time as Homo sapiens should decide to rejoin nature, some of us can only hope for the right virus to come along. Wow, right? Now that's pretty extreme, but there is a little bit of like an undertone of, at least when I was growing up, like there's a little, I think these, like I said, I don't think the climate thing is on the tip of most people's minds right now in America, at least. Maybe it is. Maybe I'm just not getting the right news feed. But there's this really corrosive tone to a lot of these things that can go off the rails, where it's like, hey, there is a genuine recognition, I think, in most people that we should be living in harmony with our natural world. Fair enough. I think that's very intuitive and right on. But it can go completely off the rails too. Like I think anybody who's trying to develop some scientific hypothesis that the best thing to do would be get rid of humans. I think they're no longer playing for the same team anymore, right? So something to watch out with, and I think that that's what's going to make this a really challenging thing. You know, we could probably teach an entire class about climate because the models and the reasons, the scientific theories for why these things happen are in some sense deeply informed by a lot of these tensions that people are feeling with respect to how humans are influencing our environments, and should we fixate on this one molecule, and if we do, how will that inform our models? And there's a really human element to the story that we tell about how the climate changes. Yeah.
I think part of that is that negativity is easier to latch onto as humans than positivity.
Yeah.
So therefore, it's easier to sell.
Yeah, I mean, getting people afraid, then you get into all sorts of political things, right? It's like, yeah,
From a commercial standpoint.
from a commercial standpoint, sure.
Just,
Yeah.
Like it's why dystopias tend to sell more than like utopia stories don't really exist.
Sure.
Humans like conflict, they like negativity.
Yeah, and I mean, it's a huge, by the way, green technology is a huge market, right? Everybody wants to feel good. Everybody wants to buy that thing that says it was made with, recycled paper, and they want to have the whatever green, like this is there's a huge force driving this. And in some sense, it's like, I get it. Like I also too want to live in harmony with nature, but you got to watch out because there's these predatory entities that are going to capitalize on that for sure. Yeah.
On the back of that, I have actually seen a lot of climate change news, and one of them is that they just declared in the last month that we've reached the tipping point,
Okay.
the official tipping point that we can't go back.
Oh no.
All the coral reefs have like lost their color.
Yeah. Well, that is scary, actually. The coral reefs are scary.
So I was kind of like wondering, what do you think
Yeah.
about that? Do you think there is a tipping point?
I mean, I think that there's like 25% of the fish in the ocean that there were, 50 years ago or something. Like, and I do think that there's terrible impacts of human industrial negligence on the world that we live in. I think it's been really bad for us. I mean, we got to ask your generation's got to ask serious hard questions, like why is our life expectancy going down for the first time? Like there's weird things happening right now on planet Earth for sure. Do I think that it's because of CO2? I really doubt it. I think it's because of the things that discussion's sort of masking. I think there's a lot of really gnarly stuff. I think I think we started building everything out of plastic about 50 years ago, and we didn't realize that plastics are shaped exactly like your hormones. And I think they're shaped like the fish's hormones, and I think they're shaped like, I think that's a huge piece of the puzzle. Plastics don't really go away very quickly. They just degrade and turn into these little pieces that end up everywhere, basically. Petroleum's the same way. It's also polymers that end up all of your cars as we're driving around. All these little particles of this petroleum from the tires is going into the water tables. It's affecting all of the critters. It's affecting the critters' food. It's affecting the food's food.
That's what I was going to say, is that all of the chemicals, we've tested so little of them together and how they react together.
Right.
And I was a hairstylist for 10 years and I quit on the back of that because of the cancer risks. And I realized that my industry, I was doing hair color all day and just pouring it down the drain.
Yeah.
And imagine like the people in the store next to me or the tire shop down the street, they're all
Yeah.
different chemicals.
Yeah.
And we've only tested a handful of them together. And so, of course.
Yeah, it's wild. I mean, like I live on a well, and it's like you get your well tested, and it's like they test for like E. coli and like 2 or 3 things, right? But there's like hundreds and hundreds, thousands of chemicals, right? And many of them quite scary stuff. So in some sense, I think we have to we're gonna have to take a really hard look in the mirror. We're not gonna be able to tell these nice little these nice little convenient stories. Like if we just put CO2 scrubbers up, that will everything will be fine. It's I think that that's misleading not only our own fate. It's not only leading us in a bad direction, but it's also screwing with the science, which hopefully I'll get to. But I don't know. Yeah.
I think another biggest thing that might happen is probably you can't really get into is for why humans are their life, the average lifespan is going down is human. It's completely related to human politics, and that's a whole conversation we can't have. But that is you add that
We might never get to Mercury, but we can have that conversation.
add that to the fact of all the other old microplastics
Yeah,
stuff.
yeah.
It's pretty clear why
Yeah.
it's going down.
Yeah, it's a multifactorial system. There's all sorts of feedback loops. It's just like climate change itself. It's really hard to point at one little thing. You're right. Humans are involved. There's different interests.
It's easy.
You really want something to blame. Humans really, really like to have something to blame. That's obviously the seed of all sorts of idiocy, ranging from racism to carbon dioxide. This is the way people think. They're like, if it was just this one person's fault or this one molecule's fault, then if we just got rid of that, everything would be fine. And it's that's just unfortunately not how the universe works. So look, we can say some interesting things though about climate. So anyways, I guess I do want to talk about climate, but climate gets wrapped, my points here, my overarching point before I move on from this, and I know we could talk about it forever, is that the scientific concept of climate change, which is actually quite fascinating and bizarre, and I hope we can talk about it a little bit just as a scientific process that is a great mystery. It gets really wrapped up with, should we take care of the planet? Which the answer is obviously yes. So those two things get tangled up in conversation a lot, and I think that that's something that we have to separate out, because the fact that the Earth's climate has changed radically over the past several millions of years, the fact that it changes radically on the order of hundreds of thousands of years, right? That's really interesting and true and bizarre, and honestly, that part has nothing to do with human beings whatsoever.
It might be prudent to call it natural climate change.
I like that. Yeah, so there's natural cycles of climate change, absolutely, and that's really quite interesting stuff. So how do we know about these cycles of climate change, right? Well, they dig out these cores, they take a circular drill, and they drill down into the Antarctic ice. And what do they get out of that? So this is a really scary looking graph. This will not be on an exam, so don't worry about it.
Oh, thank God.
So people have to reconstruct the history. So they're trying to figure out the ultimate thing that we're talking about is cooling and warming, right? How the heck do we know how cold it was 15,000 years ago? Oh, that's a really weird thing. It's not like people had thermometers, like the cavemen were walking around with thermometers, right? How do you know how cold it was? Well, this sort of sad truth is we don't really know, but we can try to estimate it. And the way that we estimate it is rather indirect and a little bit sketchy, so it should be taken with a grain of salt. But the basic idea is that we're trying to gauge essentially how fast the oceans evaporated and rained down on the poles. That's the short and sweet answer of it. So have we talked about isotopes at all in this class yet? Do you guys know what an isotope is? So all these atoms have weights to them, right, on the periodic table. The annoying thing is that these weights aren't the whole story. There's actually, for each one of these atoms, some of them are a little bit heavier, some of them are a little bit lighter. We call the heavier versions the different versions of these isotopes, right? So I'm not even going to get into the atomic science of why there's isotopes. The point is there's heavier versions of some elements and lighter versions. Oxygen's got heavy versions, it's got light versions. And what we can do is we can actually assess how much of those heavy and light versions end up in those ice cores that those guys are drilling out. And the basic idea is something like it's got to be pretty warm for the heavy ones to evaporate out of the ocean because they require more energy to get them kicked up. You can think about evaporation as like a kick, where some heated up air molecules kicking the surface of the water and pops one of them up into the atmosphere. You got to kick it harder. In other words, it's got to be warmer for the heavy things to evaporate and then end up being deposited at the polar ice caps. So that's how we know the temperature at these multi-thousand-year intervals. And we're also assuming some baseline level of deposition. So we're like, oh, well, this much comes down per year. So over time, you know, this is how we end up with the years thing, right? It's based on some average level of precipitation. But it's a rough estimate. Let's be clear about that. Nonetheless, we still see these really interesting patterns, right? We can also measure stuff like we can find air bubbles and look for actually how much CO2 is inside of these air bubbles. Now, is it perfect? Probably not. Can things escape from these inclusions? Of course. But to the best of our ability, we see these changes, at least in the precipitation levels, be correlated to temperature. We think that there's a periodicity to the temperature, for instance. So I think temperature's in red here. It tracks really nicely with CO2, again, because of the feedback loops that we talked about earlier. So this story, again, of CO2 is quite interesting because, yeah, if you look at just the last few thousands of years, it seems like CO2 has gone up precipitously. But the way that they're measuring CO2 over here is actually with actual CO2 sensors in the atmosphere. The way they're measuring it over here is from bubbles in ice. It's like, I don't know. I mean, who knows if their bubbles were like perfectly encapsulated and didn't leak any CO2 over thousands and thousands of years. Like, this is a really difficult comparison to make. So again, I actually went for a jog the other day and I took this picture. Like, this is just my street, right? Like, what is this stuff?
Oil.
Yeah, it's not good, right? But it doesn't get included in this discussion, so that bothers me. Now, if we look at the temperature discussion over if we look at the temperature map from these cores over millions of years, this is what falls out, which is completely bananas looking, actually. What do you guys make of this graph? It looks like, in some sense, it was quite warm a while ago, some millions of years ago. But like, what's up with this wavy stuff? Yeah, what's up with those spikes?
That's like I guess I would assume like ice ages basically, right?
Well, those actually only have gone on for the past 2 million years, let's say. 2.5 maybe. But yeah, it's more spiky. So okay, maybe that's part of it. I mean, maybe part of it is just the fact that these variations just get completely ironed out after millions and millions of years too, right? Maybe our data points are just much better in recent years than they were as this ice gets compacted over millions of years. I don't know.
Maybe the inverse is true.
What's that?
Maybe the inverse is true.
Or the inverse is true. Maybe the later stuff is messy for other reasons as well. We just don't know. So this is kind of, in some sense, it's the frustration, and in some sense, it's the fun of studying the deep past, because you really are left wrestling with second and third order interpretations of what things mean, and it makes it really, really difficult.
Equivalent Vostok delta T mean.
Vostok is the ice core sample.
Oh, okay.
So that's the change in temperature, I guess, the swing.
Delta temp. Okay.
Yeah. Oxygen 18, this is just the heavy oxygen that I was talking about. This is the primary readout of temperature. So I guess they're kind of like translating that into temperature over here through some formula or other.
Oh.
All right. I'm gonna have to finish this next time. There's absolutely no way I can tell this story very well, because I wanna start to play with theories for why in the world this happens. It's actually quite interesting. I'll leave you with one thing that's actually we'll circle back on this, but let me show you something. This is what happens in the North Pole every year. You can see that when it gets cold, as we would expect, the North Pole is the coldest point, right? This kind of makes sense, right? It's kind of spinning around. But what's really weird about the glaciation, can you guys see this is a model of the glaciation. The model, by the way, is informed by the impression of the weight of the glaciers on Canada and on the surrounding areas, right? Do you guys see where the glacier is centered during the last glaciation point? It's centered on Greenland. It's not centered on the North Pole. That's freaking weird. Anyways, I'll send you home with that one to think about for a little bit. We'll come back to this figure, and I want to start comparing some theories about these glacial cycles as as they refer to the natural climate change over the course of history. But yeah, there's something different than simple temperatures going on there. So we'll unpack that I guess, next Tuesday. Again, I work every day. I have no idea what day of the week it is most of the time. I'm sorry. I'll see you guys next week. Have a wonderful weekend. Yeah.